All right, we're in 10.2 now, and we're still looking at counting problems. That's all of Chapter 10, really. But what we're trying to do in this section is develop a more efficient technique for handling these counting problems than we looked at in 10.1. 10.1, we were focusing on what we call systematic listing, which we did that in a number of different ways. We created tree diagrams, we made tables, we listed possibilities kind of in different arrangements, rows and columns and things like that. But the problem with that approach is that those examples that we looked at were very, very simplified. In other words, the total number of possibilities that we had to consider in each part of a particular task were pretty small to make the listing not so time consuming. But we could very easily make a problem like that unmanageable by looking at cases where each part of a process has way more possibilities. And it becomes impractical to use those systematic listing approaches in those cases. So here's where we want to develop a much, much better tool. And it's going to be called the fundamental counting principle, which we will derive. We will talk about this in a moment. So first of all, we want to define a particular term that comes up in the fundamental counting principle, something called the uniformity criterion. So the uniformity criterion is something that we refer to in the case of a multi-part task. And as we said before, a multi-part task is a task where there are stages. You know, choosing a 3-digit code would be considered a 3-part task because you choose a first digit followed by a second digit followed by a third. The uniformity criterion is something that some of those multi-part tasks satisfy, and it's when no part in that process depends on what was chosen in a previous part. So an example of that would be this example that we did in 10.1, where we were finding that 3-digit code. Remember, the first digit was a number from 1 to 4. The second digit was a letter A or B. The third digit was a number from the set 7, 8, or 9. And regardless of what the third digit ends up being here, it's not dependent on what was chosen for my first or second digit. So what this really means and why this is important to us is because if I choose a 1 and an A for my first and second digits, then I still have the same 3 choices available for my third digit as I would have if I went with 3B for my first 2 digits. I still have 3 choices for that third digit there. Okay, an example where we don't have that criteria satisfied is the example where we were choosing let's see, where is it? Oh, same page actually. So where we were choosing a committee of 2 people. So in this case, the second choice of our person on this committee does depend on the first choice because we can't choose the same person twice. So notice when I was listing the total number of committees that have person A first, it was different from the number of people or the number of committees consisting of person B chosen first. And that's because we counted this AB as the same thing as BA. So some cases we satisfy that criteria, other cases we don't. And the ones that do satisfy that uniformity criterion are the cases where we can use this thing called the fundamental counting principle. So here's what the fundamental counting principle says, and then I'll show you again a previous example that we've already looked at why this works. So in a k-part task, k is the number of parts here, in which the first task can be done in n1 different ways, the second part can be done in n2 different ways, etc. The total number of ways to complete that task is the product of the number of ways to complete or the product of all of the different numbers of ways to complete each of those individual tasks. So this becomes more concrete when we look at an example that we've already considered. Again, back to this 3-digit code. Remember, we wanted to pick a 3-digit code where the first digit belonged to this set, 1, 2, 3, 4. The second digit was a letter A or B, and the third digit was a number from the set 7, 8, and 9. The size of each of these sets determines the number of possibilities for each stage. So if I want to come up with the total number of ways to derive a code fitting this criteria, the total number of possibilities for the first part of this process is 4. The total number of possibilities for the second part of this process is 2, because I only have 2 choices. 2 goes here. And then I have 3 choices for my third digit. And rather than create this gigantic tree diagram, I actually could just multiply 4 times 2 times 3, which is 24. Same answer, but it took me a tiny fraction of the time to get that answer. That's why we like the fundamental counting principle. It makes short work of problems that it can be applied to. So let's look at some other examples. A lock has a 3-digit code. Again, this is a similar example as before, in which the first 2 digits must be a number from 0 to 9, and the third digit must be a capital letter of the English alphabet. How many such codes exist? Well, this is similar to our previous example, but if you can picture it, creating a tree diagram for this would be an absolute nightmare. In that example in 10.1, we had a 4 possibility case followed by a 2 possibility case followed by a 3 possibility case. 4, 2, and 3. Those are small numbers. And even though they were small numbers, and going back to this, it still created a fairly big tree diagram. Now we're looking at a case where we have far more possibilities, and that tree diagram would be absolutely massive. Not fun. So instead, we just need to consider the total number of ways of accomplishing each part of this task. So again, the first 2 digits must be a number from 0 to 9. There's 10 digits from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits in total. So for my first digit, I have a total of 10 different possibilities that I can choose from. Once I've chosen that first digit, I then need to choose a second digit. And notice, there's nothing in this description that says that we can't use the same digit we can't use the same number for our second digit as we did for our first. So I have the same 10 possibilities available to me for that second digit. Fundamental counting principle says that I need to multiply these numbers. Finally, the third digit is actually a letter, and it has to be a letter of the English alphabet. There are 26 letters in the English alphabet. So the total number of possibilities is 10 times 10 times 26. This is equal to 2600. Notice that took me almost no time at all. Most of the time was just me talking through it. So this is a very, very powerful technique, very efficient at solving these problems. Let's do some more. This case, we're looking for the total number of 3-digit numbers that exist. And then there's a follow-up question. How many of these 3-digit numbers have no repeated digits? So when we talk about a 3-digit number, we do need to be careful about what digits are being considered in a 3-digit number. So, for example, the number 145 is a 3-digit number. And notice, each of these digits here can be any single-digit number, but there is one restriction that we have to consider. We cannot let the first digit, the digit in the hundreds place, be a 0. Because, for example, if I said 098, that's just the number 98. And we don't really consider the number 98 to be a 3-digit number. Even though there is a leading 0 here, we would actually think of that as a 2-digit number, not a 3-digit number. So considering that restriction, if I want to determine the total number of 3-digit numbers that exist, for my hundreds place, I actually only have 9 digits available to me. And the reason for that is because we don't want 0 to be one of those possibilities. But 1 through 9 are all okay. So for the first digit, I can use one of 9 possibilities. The second and third digits can be any single-digit number, whether it's 0 or not, because that's not going to create the same problem that we had here. So that's 10 possibilities for my second digit, and 10 more possibilities, the same 10 possibilities for my third digit. That means in total, there are 900 3-digit numbers. Okay? Now, the follow-up question here says, how many of these 3-digit numbers have no repeated digits? So this count here of 900 numbers, 900 possibilities, is including numbers like 145, but it's also including numbers like 144. That's a 3-digit number that would have been counted amongst these. However, if we want to do this follow-up question, we wouldn't want to count numbers like this one because this has a repeated digit. 4 shows up in 2 different places here. So how do we remove all of those repeated digits? Well, you don't want to go through and list them. That would be an extremely long process. Instead, what we want to do is think using this fundamental theorem or fundamental counting principle. How many choices do I have for my first digit? Well, again, same reasoning as before. We have 9 because we don't want to use 0. But now, once I've chosen my first digit, how many choices do I have for my second digit? It's not 10 anymore, because whatever I chose for my first digit, I'm not allowed to use that again. Again, because we're looking for no repetitions here. So normally there would have been 10 choices for my second digit, but I've eliminated one of them by choosing this first digit here. So that means now there's only 9 choices available. How many digits would be available for the third digit of this number? Well, I've picked one digit here and another digit here, and we know that they're distinct. So of the 10 possibilities that I would have normally had, I've used 2 of them already. That only leaves me with 8 possibilities left for that third digit. 9 times 9 times 8. If you multiply this comes out to 648. Substantially less than the total number of 3-digit numbers, but that's because a lot of 3-digit numbers have repeated digits, and we wanted to remove those. Okay? Let's do some more examples. All right, so in this example, we're attempting to put together an outfit consisting of a shirt, pants, socks, and shoes. And we have options for all 4 of those. We have 12 shirts that we can choose from, 5 pairs of pants, 20 pairs of socks, and 4 pairs of shoes, all of which can be used in this outfit. The question is, how many outfits are possible, regardless of whether they look good? Obviously, certain combinations of those are very likely to not match, and we don't really care about that. My 6-year-old son doesn't care about it, so this can be an example like, outfits that he would pick out. They can look completely ridiculous. The point is that we're just looking for a total number of combinations. You can do this with a tree diagram, and it would be an even more horrendous tree diagram than the one we thought about before. Absolutely terrible. So I'm not going to go that route. Instead, we just multiply the total numbers of possibilities for each part of choosing this process. I would choose one of my 12 shirts first. Then I would choose one of my 5 pairs of pants. And then I would choose one of my 20 pairs of socks. We're going to consider all of these 20 pairs of socks to be distinct from each other. There's something that makes each pair unique. And then I have 4 pairs of shoes to choose from. This is a total of 4,800 outfits if you do the multiplication. Okay? Again, notice how much more quickly we did that than if we had created a tree diagram. Another example, making a committee. So we, just like before, we want to build a committee, but we have more candidates to choose from, and we have more criteria to consider. So this time, we're going to build a committee. It's going to consist of 4 people, but chosen in a specific way. The pool of candidates that we have consists of 20 Republicans and 24 Democrats. And for whatever the purpose of this committee is, we want to have equal representation of both parties on this committee. So that means we want 2 Republicans and 2 Democrats to make up this committee. So the question is, how many such committees can be assembled? Again, fundamental counting principle. So let's just say we're choosing the Republicans first. When I choose my first candidate, I have 20 to choose from because there are 20 Republicans. Once I've chosen that first Republican, I now only have 19 to choose from for the second Republican in that pool. Now we move on to choosing Democrats for our committee. I have 24 Democrats that I can choose for this third committee member. And once I've chosen that Democrat, that leaves me with 23 remaining to choose for that second Democrat on that committee. And that gets me all 4 committee members with equal party representation. So this is what I'm multiplying out. This product comes out to a very large number. It's 209,760 committees. It's a lot of possible committees. Okay? Let's look at another example. Now, this example motivates the thing that we're going to talk about after it, so that's why I'm putting it here. It says, how many 4-digit numbers consist only of the digits 1, 2, 3, and 4, such that no digit is repeated? This is kind of similar to the example that we did before where we said how many 3-digit numbers are there, and then how many 3-digit numbers have no repeated digits. The difference here, though, is we're not allowing ourselves to use any of the numbers from 0 to 9. We're restricting ourselves to only being able to use numbers like from the set 1, 2, 3, 4. And not only that, we're also not allowing ourselves to use any of those digits more than once when constructing this number. Another way of thinking of this exact same problem, notice we're using 4-digit numbers. We're coming up with 4-digit numbers, and we have exactly 4 digits to choose from. That means any of the 4-digit numbers that we create will consist of all 4 of these numbers in some arrangement or another. So for example, 4, 3, 2, 1 is one possible 4-digit number we could create. 3, 2, 1, 4 is another example, 3,214. Every number has no repeated digit, but it does consist of all 4 of our choices. So another way, again, of phrasing this is that we're looking for all possible rearrangements of the 4 digits 1, 2, 3, and 4. Okay, remember that terminology because that comes up after this. So when choosing our 4-digit number, we have 4 digits to choose from for the first digit, 1, 2, 3, or 4. My fundamental counting principle says start with that. Once I've chosen that first digit, we're not allowed to repeat it. So I remove that digit from my my possible choices, leaving me with 3 possible choices for the second digit in this number. Now I've used 2 out of my 4 possible digits, leaving me with 2 choices for the next. And then finally, that only leaves me with 1 choice for my final digit in this 4-digit number. So the total number of possibilities is 4 times 3 times 2 times 1, which is equal to 24. Okay? Now this specific operation where I take a number like 4, a natural number, and multiply it to all of the natural numbers that are less than that number, 4 times 3 times 2 times all the way down to 1 like this. This kind of operation occurs a lot in counting problems, and because of that, we want to give it its own special notation. So this is where we come up to the definition of what's called a factorial. And you've probably seen this before. A factorial is exactly this operation. If you have a natural number n, then we say that n factorial is defined this way. Notice we use this exclamation point to notate factorial notation. N factorial is equal to n times n minus 1 times n minus 2 times, put a little dot right there, times dot dot dot, every natural number all the way down to the number 1. Okay, notice n minus 1 is just whatever number comes right before n. If n is equal to 10, then n minus 1 would equal 9. It's the next number down, and so on. We also oftentimes need to evaluate 0 factorial. 0 factorial, most people would look at that and think, well, that's probably equal to 0. But we define it to equal 1. Notice it doesn't quite fit this definition because you can't count from 0 down to 1. 0 is less than 1. So it doesn't really make sense to put a 0 here and somehow end up at a 1 over here. So this is a matter of definition. But it's the best possible definition for this for a number of different reasons that I'm not going to get into right now. Suffice it to say that for counting problems, we will get incorrect answers if we define 0 factorial to be anything other than 1. So let's do a little bit of work with factorial, specifically evaluating expressions involving them. First thing I want to do, evaluate 4 factorial. 4 factorial by definition is 4 times 3 times 2 times 1, and we already evaluated that. That was 24. Okay, that's easy enough, right? A lot of times, though, factorials appear in expressions that are more complicated than this one. Many times they show up in quotients. We'll see that a lot when we deal with permutations and combinations later in this chapter. So something like this, 12 factorial over 9 factorial. First of all, let me just say that 12 factorial by itself is an enormous, enormous number. 9 factorial is also very, very large. It's actually not a good idea to try and find 12 factorial by itself and 9 factorial by itself and then do the division. Obviously, with a calculator, that's not hard, but if you're doing this by hand, that's a lot more work than you need to do. So 12 factorial, by definition, is 12 times 11 times 10 times, and then we're going to have a bunch of numbers here, times 3 times 2 times 1. We eventually get down to 1, right? Okay. Actually, you know what? Let me write that a little bit differently. I want to make this a tad more clear what I'm doing. 12 times 11 times 10 times 9 times 8 times 7 times, and then we eventually get down to times 2 times 1. Okay. 9 factorial, what is that? Well, that's 9 times 8 times 7 times ... times 2 times 1. And I'm just not filling in the numbers in between because it's, it's more writing than I want to do. Rather than multiply all of this out and multiply all of this out, look for things that cancel. The 9s cancel. So do the 8s. And so do the 7s. In fact, all of the stuff in between is going to cancel as well, including these 2s and these 1s. So really, what's left? 12 times 11 times 10. Right? And that's not that bad. 12 times 11 is 132. If I multiply that to 10, I get 1,320. So you notice it's much more efficient to just look for what cancels in a problem like this. And that's generally how you want to deal with those. Last example, I'm going to evaluate two things. 5 minus 2 in parentheses factorial, and then 5 factorial minus 2 factorial. And the idea here is to show that factorials do not satisfy the distributive property. If I have 5 minus 2 factorial, order of operations says that you always do the thing in parentheses first. 5 minus 2 is 3. Then I do the factorial, which is 3 times 2 times 1. That equals 6. If I don't have the parentheses, then I'd be dealing with the factorials before dealing with the subtraction. So 5 factorial minus 2 factorial. What is 5 factorial? That's 5 times 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. Remember, multiplication happens before subtraction. If you do 5 factorial, multiply that out, you'll get 120. 2 factorial is 2 times 1, which is just 2. Subtracting, I get 118. Notice these are far from being the same number. So this goes to show that you can't just distribute an exclamation point, or sorry, a factorial symbol in and say that this is equal to the same thing as this. It's very clearly not the case. Okay? All right, so why are we talking about factorials? Well, we just saw an example on the previous page where we evaluated a factorial, 4 factorial. We just didn't call it that in that example, but that's really what was going on there. And factorials appear anytime we're looking at the total number of ways to arrange a certain number of objects. And again, that was the way that I kind of described what was happening in this example, where we were looking for the total number of 4-digit numbers consisting of these 4 digits with no repetitions. I said it's the same thing as thinking of the total number of rearrangements of the digits 1 through 4. That generalizes. So anytime we're trying to look at the total number of arrangements for n objects, then that number will always equal n factorial, for the same kind of reasoning that we went through in that previous example. So here's an example. You and 4 friends are attending a concert. How many different seating arrangements exist for you and your 4 friends? Well, again, it's you and your 4 friends. That means there's 5 people total in this group. And imagine you have 5 seats that are all next to each other in a row. How many different ways can the 5 of you decide where you're going to sit? That's a rearrangement problem. There's 5 of you, there's 5 seats to put you in, so it's basically the same thing as saying how many different ways can the 5 of you arrange yourself in a row. And according to this is just equal to 5 factorial, which we actually found in the previous example. It was 120. Okay? Factorials tell us the total number of arranging n objects. Now, the last thing we want to look at is just building off of this idea. Sometimes, if we're arranging a certain number of objects, some of the objects in that arrangement might look identical to each other. And we don't want to think of a swapping of 2 identical objects to be a new arrangement because it won't be a distinguishable one. You won't be able to see it as any different from what you had before the swap. So we talk about what are called distinguishable arrangements, which are the total number of arrangements of n objects where any two arrangements look different from each other. That's what we mean by distinguishable. Okay? So what's the formula for that? Well, let's suppose that we have a total of n objects, and we are looking for. Let's say within those n objects, there are lookalikes or repeated versions of the same object. Let's say that there are n1. That's a number, a natural number. N1 of one kind of object, N2 of another kind, and Nk, all the way through Nk for another kind of object. The formula for determining the total number of rearrangements, distinguishable arrangements in particular, is n factorial, which is the total number of arrangements, period, whether or not they look the same, divided by the product of n1 factorial times n2 factorial times all of those other factorials. So that one is tricky to wrap your mind around until you see an example, and that's how we're going to wrap up this section. Determine the total number of distinguishable rearrangements of the letters in the word banana. Okay? So we're taking the word banana and we're rearranging the letters. Now, if I look at the total number of letters in this word, there's 6. And if we're going with that factorial rule, the total number of arrangements of the letters in this word should be 6 factorial. But we know that many of those arrangements would not be distinguishable. And what I mean by that is, suppose I took the word banana and I considered that one arrangement of those letters. And then suppose I took these two A's, this one, and just swapped them. You wouldn't notice a difference in the spelling of that word. It would still be B-A-N-A-N-A. But the way that the factorial rule is counting those rearrangements, it would count that as another arrangement of those letters. So 6 factorial overcounts the number of distinguishable arrangements of these letters. That means we want to use our new rule that we just came up with. So how do we do that? Again, total of 6 letters, 6 factorial, that we're trying to find rearrangements for, divided by, and again, that rule showed a product of a bunch of other factorials down here. Those numbers are counting the things that are being repeated. So for example, I have 3 A's here. Those are 3 lookalikes. That means I need a 3 factorial down here. Times, are there any other lookalikes in the word banana? I have 2 N's in that word. So I'm going to put a 2 factorial down there. Okay? Now, we want to evaluate this and use the technique we talked about before. 6 times 5 times 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1, and 2 factorial is 2 times 1. Do some canceling. 3, 2, 1 cancels with 3, 2, 1. 2 and 4 do some canceling. This becomes a 2 up here. That leaves me with just a 1 in the denominator, which doesn't make any difference. And I have 6 times 5 times 2. That's 60. There are a total of 60 different distinguishable arrangements of the word banana by rearranging the letters. Okay? And that's going to finish 10.2 for us.